After World War II, Japanese National Railways (JNR) supported the nation's economic growth through modernization of motive power aimed at eliminating smoke emissions. This included double tracking and electrification or dieselization of major trunk lines, which rapidly enhanced transport capacity and speed. However, the sudden rise of the automobile society marked a challenging era for railways. A sophisticated taxation system targeting car owners was established, and the revenue was used to develop road infrastructure. This led to the swift construction of a nationwide road network, with paved roads spreading rapidly. Even the nationwide deployment of expressways became increasingly realistic, posing a serious threat to conventional lines. These policies hit JNR directly. Both passengers and freight were rapidly lost to road transport, leaving JNR burdened with numerous deficit-ridden lines. Its financial situation was on the brink of collapse. Although the success of the Shinkansen revived interest in high-speed rail with overwhelming velocity, the narrow-gauge conventional lines based on alignments and infrastructure dating back to the Meiji era faced inherent limitations in speed, even on major trunk lines. The maximum speed of 95 km per hour was raised to 110 km per hour for limited express EMUs and 100 km per hour for limited express diesel railcars, but the impact was marginal. Worse still, these speeds were achievable only on select upgraded trunk lines, highlighting a disappointing reality. Moreover, timetables mixing passenger and freight trains suffered from bottlenecks caused by low-speed freight services, making efficient scheduling difficult. To address these issues, JNR implemented a major timetable revision in 1968, known as the Yonsantu Revision, reinforcing track structures on key trunk lines such as the Tohoku, Sanyu, and Hokuriku routes. The maximum speed for limited express EMUs was raised to 120 km per hour, and development began on new limited express diesel railcars capable of cooperative operation at the same speed. Station facilities were also upgraded to allow long freight trains to be hauled into sidings, enabling passing passenger trains. Additionally, two-axle freight wagons underwent a major overhaul. Their running gear was converted to a two-stage link system, increasing their maximum speed by 10 km per hour to 75 km per hour. This sweeping reform, still remembered as the Yonsantu timetable revision, was, in a sense, JNR's last gamble, an attempt to offset massive deficits in local lines and freight operations with the revenue from superior services. However, the rapid economic growth and rising living standards further accelerated automobile adoption. By this time, the status of railways was steadily declining. Even the Shinkansen, once a beacon of hope, faced difficulties in extension due to soaring prices triggered by economic expansion. The enormous cost of land acquisition, coupled with the vast resources, energy, and labor required for Shinkansen construction, made it impossible to proceed with the same mindset as during the Tokaido Shinkansen era. In response, JNR desperately sought ways to utilize conventional lines for post-Yonsantu high-speed operations. Given the financial crisis, large-scale investment was unrealistic. The focus shifted to minimizing upgrades to ground infrastructure and improving rolling stock, developing EMUs that could run at higher speeds even on worn-out tracks. Due to limitations in signaling systems and braking performance, a significant increase in maximum speed was not feasible. Instead, attention turned to enhancing curve passing speed. Even on major trunk lines, curves with radii of 400 to 600 meters were common, and some segments had curves as tight as 300 meters, more typical of rural lines. If speed limits on these curves could be raised by 20 km per hour, trains with a commercial speed in the 70 km per hour range could achieve a commercial speed of 90 km per hour. On trunk lines such as the Tohoku, Sanyu, and Hokuriku routes, there are many sections where trains operate at commercial speeds exceeding 80 km per hour, and if these speeds surpass 100 km per hour, railways can regain a degree of competitiveness against expressways. When a train negotiates a curve at high speed, centrifugal force acts on the vehicle, causing it to lean outward. If this force exceeds the tipping limit, the train will overturn. To eliminate this risk, it is essential to lower the vehicle's center of gravity as much as possible, thereby increasing safety margins against overturning. Even if a train does not overturn, passengers experience a lateral force that throws them toward the outer side of the curve, resulting in an uncomfortable ride. Increasing the cant angle on curved track would mitigate this discomfort, but excessive cant creates instability if a train stops on such a section. Because freight trains whose high centers of gravity share these lines must also run, major cant adjustments are restricted, and the cost of extensive track modification is unrealistic. Instead, the solution is to tilt the car body inward by an angle equivalent to the cant deficiency, effectively compensating for the lack of superelevation. With this approach, even when a train passes a curve at speeds beyond the cant's design, the resultant forces on passengers act perpendicular to the floor, eliminating the sensation of uncomfortable lateral centrifugal force. Another challenge arises when wheels attempt to proceed straight through a curve. The wheel flange presses against the rail to steer the train into the curve, thereby exerting a lateral force on the rail. Since rails are fastened to sleepers, this lateral thrust imposes significant loads on the rail fastenings. If these loads exceed their limits, damage occurs. At that time, rail spikes securing rails to wooden sleepers remained widespread even on major trunk lines and dominated rural routes. Unless the line was fully upgraded with closely spaced concrete sleepers, it was imperative to minimize these lateral forces on weaker track. Some solutions involve forcibly altering bogie alignment or shifting the center pin position to balance lateral forces between the front and rear axles, but the most effective measure is reducing the overall vehicle weight. Consequently, the proposed concept was a lightweight train set equipped with a car body tilting mechanism and bogies featuring centerbowl mobility and steering functionality. Two primary tilting methods were considered: forced tilt using air springs or hydraulic actuators, and a pendulum system that harnesses centrifugal force during curve negotiation. Odakyu Electric Railway, which contended with severe curvature, had long pursued articulated and lightweight car designs and conducted early trials of forced tilt systems. However, the sensor and control technologies of the era could not deliver practical levels of precision and safety, preventing implementation. Meanwhile, JNR focused on the pendulum approach. Building on prototype bogie tests on the Karakachi trial line in Hokkaido, they developed the Kuemoha 591 test EMU and commenced extensive running trials. The pendulum tilt principle itself dates back decades, vehicles suspended from high-mounted stanchions on the bogie, allowing the car body to swing like a literal pendulum through curves. On the North American turbo train introduced in another video, this pendulum system was already in practical service, and research was underway in several countries. JNR adopted a design in which rollers mounted on the bogie support the car body, allowing it to rotate freely. In Karakachi trial line tests, a link mechanism had been used to tilt the car body, but friction proved excessive. To solve this, engineers turned to the rollers employed when shifting an electric locomotive's middle bogie laterally. Overcoming many challenges, they succeeded in simplifying the complex structure. They set the car body rotation center high above the rail, essentially the same pendulum principle of hanging the body from a lofty pivot. Although these pendulum systems required no elaborate detection or control technology and were relatively easy to implement, they carried serious drawbacks. In both pendulum and roller tilt schemes, the rotation center sits well above rail level. When the body swings outward in a curve, its center of gravity shifts outward too, increasing overturning risk. By contrast, forced tilt systems can place the rotation center below the center of gravity, so during tilt the center of gravity moves into the curve, advantageous for high-speed curve running. In other words, the pendulum approach is inherently disadvantageous for high-speed curves. To mitigate this, JNR lowered the car body center of gravity and simultaneously lowered the rotation center to reduce overturning risk. Another issue is friction in the suspension or roller mechanism. Pendulum motion only begins once centrifugal force overcomes this friction, so the car body moves abruptly after entering a curve, subjecting passengers to sudden lateral accelerations that upset their equilibrium and often induce motion sickness. Nevertheless, the pendulum system had benefits absent in forced tilt designs. Its rotation center roughly aligns with seated passengers' head height, so it does not impose unnatural lateral accelerations on the vestibular organs. Also, in EMUs, forced tilt can cause pantographs to lose catenary contact, whereas the high pivot of a natural pendulum allows minimal lateral pantograph displacement, reducing dewire risk. Despite remaining challenges, the QMOHA 591 test EMU delivered excellent overall results. Curve passing speeds improved by plus 20 km per hour over the standard, and up to plus 25 km per hour on well-maintained track. That 15 to 20 km per hour boost over high-performance limited express criteria promised a dramatic speeding of the Tohoku main line. Then, suddenly, construction of the Tohoku Shinkansen was approved, leaving high-performance pendulum EMUs with no suitable trunk line deployment, a major upheaval. With robust main lines ruled out, the project shifted to sub-trunk lines with fragile track structures, throwing the plan off course. The 20M2 car pendulum EMU, modified for trials, ran performance tests on the Kagoshima and Shinetsu main lines. Yet line authorities would not permit high-speed running under the burdens of dual-voltage equipment. In the end, JNR set targets of plus 20 km per hour over standard timetable speeds on sections with good track conditions, and plus 15 km per hour elsewhere. While these improvements only plus 15 km per hour or plus 10 km per hour above high-performance limited express criteria were somewhat modest, JNR decided to pursue thorough weight reduction on DC-only EMUs and to reinforce track where speed goals remained unmet. AC traction equipment deemed superfluous was stripped away, giving rise to the Agile 381 series tilting EMUs. Facing tight finances and uncertainties around new technology, JNR retained conventional resistance control and abandoned 130 km per hour operation, yielding minimal time savings in favor of a prudent 120 km per hour limit. Systems like the independent regenerative brake and field chopper control, originally added to boost adhesion during rheostatic braking, were omitted to simplify the design and cut costs. Instead, the controller was revised so that, in weak field control, it jumped instantly to notch 3 from notch off before stepping through remaining notches, partly mitigating the sawtooth operation losses typical of resistance-controlled trains. Though non-contact electronic circuits were adopted for parts of the control logic, most switching contacts remained mechanical to ensure reliability. The 381 series featured a 5-degree tilt angle 20 cm higher pivot than the QMOHA 591 and reverted to a fixed pantograph rather than a movable type, omitting many experimental features of its predecessor. To maintain a low weight of the train, the car body was built from aluminum alloy, the first such use on a long-distance JNR EMU. This lightweight construction suppressed lateral forces on curves, allowing JNR to omit complex bogie features like centerbowl mobility and steering, yet still operate on less robust track. Compared with the 183 series DC Limited Express EMUs, then the standard form of DC Limited Express EMUs, the 381 series achieved a 5-ton weight reduction. Axle loads under load were lowered by over 1 ton, and motor cars also shed 10.5 tons of AC apparatus, resulting in significant weight savings over the QMOHA 591 and helping to reduce track load. Air conditioning units, installed under the floor as on the QMOHA 591, required carefully designed ventilation ducts to maintain cooling performance and a low center of gravity. The 381 series debuted on the Chuo West and Shinetsu lines, electrified with equipment to accommodate tilting EMU pantograph displacement. In June 1973, 1 month before revenue service, various performance tests were conducted on the Chuo West line. Acceleration and brake trials were successful. From 125 km per hour to stop, both maximum service braking and rheostatic break-off stops occurred within 600 m. On a 25 per mile gradient, for M2T and 3M3T formation started under a 430A, 20% overcurrent, limit. Although details on the 3M3T makeup are unclear, test results confirm its launch capability. In 2M4T tests with a 500A limit, starts succeeded but acceleration stalled. Overall, for a Revenue 6M3T set, even with one unit cut, standard current limits enabled reliable starts, confirming operational feasibility. Thus, the Nagoya-Nagano run, which had taken nearly 4 hours with Kiha 181 series limited express EMUs, was cut to the low 3-hour 20-minute range by the 381 series tilting EMUs. Although 2 round trips of the 181 series remained, total daily services leapt to 8 round trips, delivering a dramatic shift. With dining cars removed and criticism of severe swaying, the economic impact of the 381 series EMU speedup was nonetheless substantial. Limited express ridership on the Chuo West line rose to 2.5 times year-on-year. Including the effects of replacing and adding rapid services, total patronage on limited express and rapid trains increased by 10%, confirming the draw of faster services. Passengers, relieved of waits of nearly 4 hours by a reduction of over 30 minutes, even inquired whether a special surcharge was required. Some suggested levying a tilting surcharge, so high was the acclaim. Yet complaints about unnatural swaying remained persistent. The pendulum train label itself was said to reinforce negative impressions, prompting proposals to retire the name. Even veteran chief conductors intimately familiar with the line's geometry were initially unsettled by unpredictable motions. Though they soon acclimated and complaints eased, the swaying issue cast a long shadow. The 381 series deployed on the limited express Shinano surpassed performance expectations, uplifting morale among staff along the once isolated Kasoji Mountain corridor and replacing feelings of abandonment with renewed hope. Demand grew for still more services, train lengthening to 12 car formations, and deployment on the similarly profiled Chuo East line. Plans emerged to replicate this revenue-boosting model nationwide, including requests for AC-only tilting EMUs and even hopes for a high-speed network on electrified rural lines amid struggling gas turbine projects. In reality, JNR's finances could not accommodate the required additional investments. Track realignments, insertion of eased curves, and structure reinforcement, so tilting train expansion fell short of aspirations. 5 years later, the 381 series entered the Kisei main line, and 9 years later the Hakubi line a pace too slow to deliver meaningful speedups. On the Hakubi line, surplus rolling stock was initially rotated to cover services, reflecting the severe shortage. Since further speedup was not feasible under these conditions, the 381 series tilting EMUs were introduced. But no additional 381 series orders followed, and no subsequent evolution of the type occurred. Meanwhile, even the bloated, complacent JNR recognized its dire state as privatization loomed. Research and development into the benefits and challenges of natural pendulum tilting demonstrated by the Kuemoha 591, 381 series, and Kiha 391 continued steadily, only to blossom after the JR transition. In one such effort, 381 series speed trials recorded 179.5 km per hour in a 6M2T formation. Although bogies and pantographs had been improved, this run showcased outstanding hull performance and, after 25 years, reclaimed the conventional line speed record long held by the Kuemoya 93,000.